much all of you for being here, and we'd like to thank especially the OMICS group to have the opportunity to present some of the work that we are doing at the University of Santiago de Compostela in Spain in a new research center about chemical biology and molecular materials. My research group is very much interested in the development of new antibiotics, particularly in antibiotics with a new mechanism of action. What I will try to show you today is how we apply different computational, structure, and chemicals tools for the development of new antibiotics. As you probably might know, the discovery of the penicillin and many other natural antibiotics was one of the most important achievements of the last centuries. And after that, the pharmaceutical industry provided us many compounds that were very active, and in fact nowadays we have a good arsenal of antibiotics. However, from approximately from the 60s, the research in this area has been decreased a lot, because it was thought that we have enough compounds, and also because due to economic reasons they move on into a more profitable areas like cancer or medical disease. But the problem is that nowadays we have a quite increased amount of resistance to antibiotics due to the misuse and abuse of antibiotics, and also for the normal behavior of the bacteria. Then we need to discover new compounds, and particular compounds with a new mechanism of action. And then nowadays there is quite a lot of interest in this area once again. One of the ways that we have been very successful in applying new antibiotics is try to deal with processes that are essential for bacterial survival. In this context, there is one pathway that attracts very much our attention, that is the shikimic acid pathway. That is because it is present, it is essential in many microorganisms, and it also is present in fungi, plants, and also in certain parasites, particularly the ones that are related with malaria. This pathway is not present in mammals, what is very important for that. And a good example of the potential of the pathway is glyphosate, this compound here, that is the inhibitor of the last enzyme of the pathway, the EPSP synthase, and it has proven to be active against malaria as well, apart from being the main component of many well-known herbicides. The pathway consists in 7 enzymes that transform the erythrose phosphate and phosphoryl pyruvate into chorismic acid, which is the precursor of the aromatic amino acids and many other aromatic compounds that are like, for instance, folate cofactors and vitamin A and K. In our group, we have been focused on 2 of the enzymes. The third one, the dehydroquinase, that I will talk to you today. And also, we have been working more recently in the shikimic kinase enzyme, that I don't have time to explain to you our work. We have today. We have been interested in these 2 enzymes because they are essential in important pathogenic bacteria, in particular in Mycobacterium tuberculosis, the causative agent of tuberculosis, and also in Helicobacter pylori. As you might know, the World Health Organization has been considering tuberculosis as one of the priorities in research, and is responsible for 2 million fatalities per year, and is particularly important in that persons that they have a compromised immune system. And the treatment that we have today is very much is not very good because it requires quite long periods of treatment with a cocktail of drugs. Helicobacter pylori is also very important because it's involved in chronic gastritis and duodenal ulcers and has been classified as a type 1 carcinogen. And it has been, in the recent years, there has been a lot of increase of the resistance against calcitromycin, that is the standard antibiotic for those. Our approach to the development of these compounds is starting from the enzymatic mechanism. We study quite in detail the enzymatic mechanism to try to dealing with the essential residues involved in the process. In this case, we try to avoid the possible resistance of the enzyme. We use docking studies to design our molecules and then after that we synthesize in the lab. And we also perform structural studies to prove our hypothesis, and we combine also with molecular dynamic simulation studies. As I will show you later on in the talk, the dynamic of the enzyme is very important, and it's a good way to have to provide the inhibition. The type 2 dehydroquinase enzyme is catalyzes the reversible dehydration of the hydroquinic acid into the hydroshikimic acid. It has been known that there are two essential residues involving in the process, that is a tyrosine and also arginine, that is located in a flexible loop that covers over the active site after substrate binding. And what is believed is that the tyrosine removes the acyl hydrogen and it is formed an enolate. It was quite a lot of discussion about if it was an enol or an enolate. This enolate is stabilized by a water molecule that, as I will show you later on, has been very important in this stabilization, and it is quite unusual. And the last step is the elimination of water that is involved in histidine acting as a proton donor. In this mechanism, it was quite unusual to have a tyrosine as a base, and it was quite a lot of and we were quite curious how, I suppose it will be a tyrosinate, how it will be formed. And also it was another important question, how the arginine is involved, why it's so essential for catalysis. To get an insight on how it was going on here, we performed some molecular dynamic simulation studies and also quantum mechanical QMM studies to get more details about the process. For that, you have to consider that the enzyme is a dodecamer, but it's a trimer of trimers, and the trimer is the minimum catalytic unit that we use for these studies. We have used water truncated octahedron of waters, and this makes a quite heavy from the computational point of view system, but it works. It's the only way that it works. We have taken into account quite particularly the protonation of taste of the histidines involved in the process. Our results show that the Michaelis complex for the Helicobacter pylori enzyme, we identified that is aspartate from the neighbors unit that is involved in the deprotonation. Excuse me. This deprotonation, we found that it is mediated by a water molecule. And it was very important to find that the arginine has several roles. One, it will be the reducing the pKa of the tyrosine, also with these two arginines. And also, it was by the formation of a cation-P interaction, it was controlling the right position of the tyrosine for the proton extraction. We found also, quite surprisingly, that in the case of the Mycobacterium 1, it was the protonation takes place directly without a water molecule. This was also proved by solvent isotopes effect, a proton inventory. As you can see here in the Mycobacterium 1, it was only one protogenic proton involved in the whole process, and for the Helicobacter 1, it was more than one. Also, we have performed some mutagenesis studies to prove that, in fact, this aspartate was essential for catalysis. As you can see here, the enzyme is completely dead after the mutation. We have also studied how it was the turnover of the enzyme, and we found that the arginine is also involved in taking off the product from the actin site, and also after a large conformational change around here that is involved, these two arginine, they are conserved in the process. As you can see here, after this change, the arginine is taking off, pulling off from the carboxylase, and it is controlling the exit of the product from this side of the active site, and as it was something that it was completely unknown. As a summary, a picture of the enzyme completely active will be a completely closed form of the loop, with the two essential residues very close in space, forming a cation-P interaction between the arginine and the tyrosine, and also the intermediate was an enolate in which the arginine is stabilizing together with a water molecule the process. What I will show you today is how we apply, how we made different compounds trying to avoid this picture that I told you already. And I will show you a few examples that the compounds that targeting the loop conformation, particularly the two essential residues, and also how we apply this water binding pocket that is very important. If the enzyme removes the actual hydrogen, we thought that in the first time that if we change this hydrogen for another different from hydrogen, maybe we will have inhibitors. But when we were carrying on this docking study, we realized that if we also use the equatorial substitution by a benzyl group, these two aromatic rings, they come together in space and they interact quite nicely. Then we decided to study the both cases, and we perform different. We include different benzyl groups with different substitution, and also we test with no aromatic rings to see that they were less active. As you can see here in the table, indeed, these compounds proved to be quite good inhibitors of the enzyme, particularly for the Mycobacterium 1 in the low nanomolar range, the Km from this enzyme in the micromolar range, and the most active one was the benzothiophenyl group. More surprisingly, the ones that they still have the hydrogen to be removed by the enzyme, they were even more active than the previous one, and in both cases we have quite better results, particularly the paramethoxy and the benzothiophenyl group. We performed some structural studies to prove our data, and also to get an insight on how it was going on in detail with the enzyme. And what we found is that we were able for first time to solve the full loop of the enzyme, that it was not possible until then, because the tyrosine was on top of the paramethoxy methoxy group. And also, as you can see here, in this overlap with another crystal structure what it was available, in which the arginine is inside of the active site. As you can see here, the benzyl group is taking the place of the arginine. Then, as you can see here, what the compound does is just reduce the flexibility of the loop and avoiding the entrance of the arginine into the active site. We have been also possible to get the crystal structure with the perfluoro derivative in the axial substitution, and in this case what it happens is that the loop is also not flexible at all, because interaction with the arginine between the fluorine atoms and the arginine, and also with the tyrosine, is just reduce and control the position of the loop. And maybe this is why it's so potent. Also, with the paramethoxy 1, we found is that the arginine is out of the active site. In this other approach, we have made some enolate mimetics. Professor Abel from Cambridge University described that these very simple compounds with a double bond in the 2 and 3 position were inhibitors of the enzyme with a Ki quite high. He described the crystal structure of the compound, and what we saw is that it was a quite reasonable whole that we can apply new. We can make new compounds and maybe to try to get more potent inhibition. And for that, in our first time, we made different analogues with a very simple chain, and at the end with aromatic ring, because it was good for us in our previous results. And as you can see here, all the compounds were very potent in the nanomolar range for the two enzymes. The crystal structure of this shows that the aromatic ring is on the top of the tyrosine, and the loop is completely described, and with once again with the arginine is completely out of the active site. Later on, we were able to describe the crystal structure with the Mycobacterium 1 at a very high resolution, 1.5 angstrom. This is allow us to describe the position of this water molecule. And this is a surprise us quite a lot, because we have two oxygen atoms very close in space. And we thought that maybe this interaction with the water molecule was quite good for the potency of the analogues. Then we decided to explore if it will be possible to change, and how was the effect of this interaction. For that, we changed the oxygen atom for a carbon, also to make the compounds to be more suitable for in vivo studies, and the results show that indeed the replacement of oxygen by a carbon we lose quite a significant amount of inhibition potency. However, this can be decreasing if you extend the two space by a 3 carbon chain, because in that case the aromatic ring reaches a region of between the two chains that we know that is very important for selectivity and also for potency. And it happens the same with the benzothiophenyl group. As you can see here, we lose it with the simple exchange, but we recover quite a lot if we replace it by a 3 carbon. We performed some molecular dynamic simulation studies, starting will be the two compounds with the oxygen and with the carbon, and after the simulation with the oxygen, it keeps in the place. But however, when you change it for the carbon, the compound, the ligand escapes from for the water binding pocket, and we think that this is the reason why we lose the activity. Thinking that it was very important, this water binding pocket, we decided to explore a little bit more the potential of that. And we synthesize a few compounds, very simple ones, with a simple carbon with a OH at the end, and also these other two, that they were a benzyl group with the two possible stereochemistry of the OH. As you can see later on, this stereochemistry has been very important for our purposes. In the crystalline structure, as you can see here, the simple compounds with a regular chain with the OH, it doesn't go into the water binding pocket. And maybe we think that this is the reason that we have no so good inhibition. It was when we got the benzyl derivative, it was very important, the stereochemistry. For the ones with the S stereochemistry in the chains, the OH goes into the water binding pocket, but also the stereochemistry does not allow to put the benzyl group in an extended conformation. That is also possible in the other one. We think that this is much better for the inhibition. This was much clearly shown with the chlorinated ones, that we were not able to crystallize it, but we explored it by molecular dynamic simulation studies. As you can see here, the S takes off the place of the water molecule, and for the air it is interacts with the pocket, but it not replace the water. And we think that this is the good way. We have been, these compounds require by the enzyme very polar substituents in the molecule. This was a challenge to get into in vitro studies, but for that we perform a product approach to try to get inside, and it was very important to look for the stability of the ester. Methyl groups were not good because they hydrolyzed too quickly. Ethyl groups, they were much better, but the good ones with the propyl groups in the ester to get reasonable MIC values. You can also play around with the OHs, but we think that these are the best compounds for the activity. As in summary, what I show you here today is that we can get the inhibition of the compound by either trying, I didn't have time to show you today, that we have described compounds that they are not allowed to close the active site, and this was already completely in an open conformation. I have shown you also ones that they perform a very close and tightly loop in a no flexible manner, and which the perfluoro derivative is in, making like a sandwich between these two essential residues. And in these two examples are ones that they perform like a semi-open form of the active site, in which the arginine is completely out of the active site. In summary, we have identified several active compounds against Mycobacterium tuberculosis and Helicobacter pylori. For our design, we have used several tools like the mechanism of action of the enzyme kinetic, molecular dynamic simulation studies, quantum QMM studies. We have described several structural studies that showed our hypothesis. The strategy is always the interaction or the direction of the normal behavior of the enzyme, and also the motion of the enzyme. And we have the Bello products approach for in vitro studies. And we think, I hope that I can convince you that we think that the dehydroquinase is a good therapeutic target. I would like to finally thank the people involved in the work, that they are very enthusiastic people from our lab. Particularly, I would like to thank the work of Emilio Lence in the computational side, and also the work of Veronica Prado and Maria Maneiro in the synthetic part, and other new people that enjoyed the people more recently. I would like to thank my collaborators, Professor Hawkins, who provides all the enzymes that we use in these studies. Dr. Van Marray, who we collaborate in the structural studies, and Dr. Jose Ainsa, who performed the in vitro studies, and Professor Federico Gago, with we start these molecular dynamic simulation studies. We like to thank the institutions that provide the financial support for these studies on the facilities of the computational, the supercomputers, the CESGA, and also the ability to access the synchrotron facilities in Europe. And I would like also thank you for your kind attention.
Thank you. We have some time for questions, so if anyone...
That's very impressive talk, obviously. A couple of slides earlier, you mentioned confirmation comparisons like closed versus open. So my question is very naive. You probably mentioned that, but probably I didn't catch it. So I just wonder, the confirmation closed and open is defined by crystal structure or by simulation?
With both, because by simulation studies you can see the movement, but also we have crystal structure in all the different conformations. The pictures that I have with the electronic density around the ligand are crystal structure. The others are simulations.
Molecular dynamic simulation?
Sorry?
It's QMMM or just MD or just a confirmation sample?
We have performed some molecular dynamic simulations, and for the mechanism studies we do QMM studies.
Okay. Any other question? Please raise your hand so I can take the mic to you. Okay, one over here. Don't make me run too much.
Thank you very much for your talk. I recognize there's some differences between the pylori and the tuberculosis parasite or bacterium. What is the homology for these two bacteria?
Sorry?
What's the homology between the sites there for pylori and tuberculosis?
Do you mean the selectivity, the compounds between the two?
Yeah.
I mentioned quite rapidly, maybe. The enzyme is the active unit is a trimer. And we believe that the difference are in the different sequence between the two chains, that they are a little bit apart from the active site. Depending on how these aromatic parts interact with this difference, it makes more selective or less against one until the other. And the big difference is how the loop is movement. The loop movement. The Mycobacterium one is very flexible and it moves quite fast, and the Helicobacter one is like very slow, and there are significant differences. But the essential residues and the conserved residues are exactly the same. Yeah.
Thanks.
Any more questions? Oh, I'll pass it him and then over.
Hi. Yeah, very nice talk. So you postulated that the pK of the active tyrosine is actually lower because of picat ion arginine. So has there been any animal work to determine what's the pK of this tyrosine by C13?
We didn't do it by NMR because it was quite challenging for us. We estimated, and it drops around 7 when everything is very close together.
Okay. And what's the distance between the guanidine and the tyrosine?
I think it's around 3.5 or 3.8. I don't remember exactly.
Right, that's very close. Yeah. Thank you.
Okay. And then we had a question in the back.
Did you find any correlation between the IC50 and MIC for your compounds against both MTB and the other bacteria?
We are working on that. I think we lose quite significant amount of the activity when we go inside. As well, it's difficult working with Mycobacterium because you have this is a double like a double entrance, and we think that part of the compound is losing during the entrance. But
any more questions? No? Okay, thank you very much.
Yeah.
Thank you.
Yeah.
Thank you. So I'll